The equation we derived was actually shape number NSH, which was n root q by gh power 3 by 4. That will be fully non-dimensional. Whereas in the field, people use specific speed denoted by n root q h power 3 by 4. G is removed, and with that the values you get is good numbers like 10, 30 or 500 like that. If you divide this by another G, you get some fraction and things like that. So this is what is used, and for this n should be in revolutions per minute, not revolutions per second or radians per second, but revolutions per minute. Q is meter cube per second, h is meters. So here you have different types. 10 to 30 is slow speed impellers, 30 to 50 is medium speed, 50 to 80 is high speed. So they are all centrifugal pumps. When the specific speed is 80 to 160, you go for mixed flow pumps, and when it is 110 to 500, it is axial flow pumps. Okay, so if for the given duty, if you get the specific speed value to be say 50 to 80 range, you have to go for the centrifugal pump design only. If you don't uh, hello, can you see that? Okay.
Yes.
So if you don't design a centrifugal pump, and instead if you design an axial flow pump, the efficiency may not be that high. So these numbers, they are related to the corresponding shapes that produce very good efficiency. Okay, these numbers provide the meridional shape. Okay, we had in the earlier class itself introduced the meridional cross section. Okay, the cross section containing the axis. Even our classification, axial, radial, and mixed, depends on the flow path in the meridional section in the rotor or the runner. Okay, so these numbers provide the meridional shape for the most efficient pumps. The main pumping duty is Q the discharge and H the head. So by selecting suitable value of N, one can design centrifugal or axial. That means there is some leeway, by choosing N, you can go from centrifugal to axial like that, but N also there could be limitations. You can't have extreme values of N. So for a particular duty, sometimes you may have to go for centrifugal machine, and for some you may have to go for axial flow pumps. Okay, now suction limitation. Okay, um, uh, now take this case. Okay, you have a sump filled with water, and a pump draws water from that. There's a motor connected to the pump, and at the exit of the pump there's a valve. Now you start the motor, open the valve, the pump will start pumping water. So this type of suction is called flooded suction, where the pump is kept below the water surface. Okay, in flooded suction, the pump is kept below the water surface. There is no suction problem here. Now take this case. The pump is kept above the water surface. Now here also, you start the motor, open the valve, the pump does not pump water. Why? As you see that, you need an operation called priming that has to be done before starting the pump. And what is this operation? It is filling of the suction pipe and pump casing with water. Now take this case. So here also you have a sump, the same pump. The suction head is 5 meters. Now for priming, you have a small extra fitting. So a small tube, and in the tube there is a small valve is there. Then a funnel is kept through which you can pour water, and you can see that the complete suction line and the pump casing is filled with water. And you see at the bottom of the suction pipe, the red color one, that is actually a strainer that is a filter plus a small valve. This valve will allow water to move up, but it will not allow water to fall down. Okay, so it's a foot valve, it is called, because it is kept at the bottommost position. So now you have to prime it. For that, you have to pour water through the funnel there, and once you find that it is full, the water in the funnel will not flow inside. You can now start the motor, open the valve, and the pump will start pumping water. Now take this case. You have again a sump. The pump motor is kept at a height of 15 meters. After priming, start the motor, open the discharge valve. Well, I have not shown a valve here. I missed it. The valve will be there most probably. It may not be also there. Now the pump does not pump water. Why? It is primed. You have a foot valve in the bottom and it is primed. This is because of suction head limitation. Okay, this will be discussed in the next slide. See, you have the suction head limitation, that is water in the sump is not pulled up by the pump, but it is pushed up by the atmospheric pressure. This is what is very, very important to understand. The pump does not pull the water up. It cannot exert any pull force, but the water is pushed up by the atmospheric pressure, which is acting on the surface of water in the sump. This pressure only produces the barometric head, which is around 10 meters of water column. So you are all familiar with barometers for measuring atmospheric pressure, and the most common barometer is the mercury barometer. So with mercury, you get about 760 millimeters of water column, or 0.76 meters of mercury column. That is called the standard atmospheric pressure. It might vary at higher altitudes. It may be less. In some places, it may be a little more depending on the air currents and all those. Now, if I consider a barometer made out of water, the barometric column will be 10.3 meters. So the atmospheric pressure on the water surface will be able to push the water up to a column of 10.3 meters. Now above that, I have left some space. Some vacuum will be there, maybe filled with the vapor pressure, not full vacuum. In some places they call it the Torricellian vacuum. So above that, some vapor pressure will be there. Okay, because corresponding to temperature, vapor would have formed, that is, water would have vaporized. So corresponding to the temperature, the vapor is there at the top and it will exert a vapor pressure. Okay, now coming to the suction head limitation. When the suction lift Hs is more than 10 meters, water cannot flow into the pump to get energized by the pump. Okay, so if we have a 10 meter barometric tube, water will rise up to only 10 meters. Even if the height of the barometric tube is 20 meters, water will go up to only 10 meters. Above that, the vapor pressure or vacuum is there. So in the suction, maximum height you can provide is about 10 meters. That also is not exactly 10. You have to give way for the vapor pressure and the head losses. Okay. Well, now we will see the centrifugal pump characteristics for constant speed. Okay, so this has to be done in the laboratory. You have the centrifugal pump connected to the motor and the suction pipe. In the suction pipe, you will have one pressure gauge. Delivery pipe also, there is a pressure gauge. Now, depending upon the valve position, you can control the volume flow rate. Okay. Now, already we have seen the head characteristics. You have maximum head, when the discharge is 0, it has a particular name. So it's called the shut-off head. Then when you open the valve, flow will take place. Correspondingly, the discharge will start increasing. You will find that the head will be decreasing. And for each situation, one can measure the power supplied to the motor and maybe multiplied by some efficiency. You can find out what is the actual power given to the pump. Then one can calculate the overall efficiency. That also can be plotted. So this is general variation. Now you have the maximum efficiency point I have indicated. So corresponding to that, you will have a head, you will also have a power and all those things. That is supposed to be the design point. All other points, even discharge above or below, they are all off design points. Some pumps will have always duty along the design point. Some may have off design duty also. So in this, essentially the speed of the pump is kept constant. So it's a constant speed operating characteristics. Now the head versus discharge for 3 different speeds. So if you find out the head versus discharge for different RPM, okay, so you should have a method of varying the speed of the pump, or rather the speed of the motor. So if you keep the speed at 500 RPM, you get the curve, the bottommost curve. So you have limited shut-off head, then the discharge is also limited. When you increase or when you double the speed, you will find that the head has increased, the shut-off head has increased, correspondingly the discharges also will increase, the power required also will increase. Then you have another curve that is corresponding to 1500 RPM. So there the shut-off head is more, the final discharge is also more. Okay, so this type of characteristics is called the head discharge characteristics of the pump characteristics. Now here I am showing the system characteristics. Okay, you have a pump system. The pump is there, the motor is there. Okay, the suction is connected to the sump. Some pressure gauge is there at the exit. Then a valve is there. Okay, here there is no static head that is in the discharge. It is at the level of the water in the surface, in the sump. Now I have given 3 curves here. So each one corresponds to the particular say valve position. So you keep the valve position same. Now to send more discharge, what you have to do is increase the speed of the pump. Correspondingly, the head also will be more. So more head, more discharge. Okay, that is the first valve position. Now corresponding to another valve position 2, you get another curve. Little consideration will tell you that for position 2, you would have closed the valve a little more. Okay, then for third position, the valve is little more closed. So you have 3 system characteristics. Okay, earlier we had seen 3 pump characteristics for different speeds. So now you have 3 system characteristics. Okay. This is another set of system characteristics. You find that the system characteristic starts with some static head, Hs. You can see that the water level is there in the sump. The final flow level is always at a height Hs. So the pump has to minimum work to produce the head Hs. Okay. So that is some sort of a minimum starting speed in which you produce a head Hs. Now again, for 3 different valve positions, you will be able to get 3 system characteristics. Okay, so these are system characteristics with static head. The difference you can see in the previous one, the system characteristics start with 0 head, but in this, the system characteristic starts with a finite initial head Hs. Any doubt so far? Okay, I'll move on to the next one. this is important. The pump system interaction. Okay, you have a pumping system, a pump, a motor, the water in the sump, then the exit valve is there. Okay, you get the head discharge characteristics, head versus discharge. So the pump will be run at a constant speed. Okay, and you see the red line, that is the pump characteristics, and the valve also will be kept at a particular position, and you have the valve characteristics or the system characteristics. Okay, you find that there is one intersecting point. We say that okay, so you have the system characteristics, you have the pump characteristics, and both will intersect at a point. So when this pump works now, it will produce a head equal to H and a discharge equal to Q given by the intersection point. Now you see a pump system interaction for three different system characteristics. You have a single constant speed pump characteristic, the red one, and you have three system characteristics. Okay, system characteristics 1, system characteristics 2 and 3. So you can think of three intersection points. So at one valve position, you will get the operating point OP1. So correspondingly, you have Q1 and H1. If you close a little more, you will move over to the operating position 2, where you have a slightly reduced discharge Q2 and a higher head H2. If you close the valve a little more, you move over to the operating point 3. Correspondingly, you will have a higher head H3 and a lower discharge Q3. Okay, so this is the pump system interaction for three different system characteristics. Now you see pump system interaction for three different pump speeds, but a single system characteristics. The single system characteristics is indicated by the green line, and you have three pump characteristics denoted by the three red lines. So the top one is the pump characteristics 1 for 1500 RPM of the pump. The next one is the pump characteristics for 1000 RPM. The next one is the pump characteristics for 500 RPM. Now you have the intersection points. The first operating point 1, which will give you a head of H1 and a discharge Q1. The second one, you will get a reduced discharge and a reduced head. The third one, you will get further reduced discharge and a reduced head. Okay. Now pump system interaction for two pump speeds and two system characteristics. Okay, the two pump speeds, one is 1500 RPM, the other one is 1000 RPM. The two system characteristics are SE1 and SE2. Okay, so the valve is indicated. You find that there is a static lift. That is why the system characteristics start from a particular height. Okay, now again you see many intersection points, the operating points, the operating point 1, 1 corresponding to system characteristics 1 and pump characteristics 1. Then here you have the operating characteristics 2, 2 corresponding to pump characteristics 2 and system characteristics 2. So correspondingly, you will be able to identify what is the head available and what is the discharge available in these situations. Any doubt so far? Okay, are you able to hear?
Yes, sir.
Yes, sir.
You are able.
Yes, sir.
So no doubts so far. Okay, I'll move on to the next one. Okay. Now the net positive suction head. See, the pump users, manufacturers, they talk about net positive suction head. Okay, it is connected with the suction side. Okay, the NPSH is defined as the total absolute head above the saturated vapor pressure head corresponding to the liquid temperature. Okay, so NPSH is the total absolute head. That means at the suction point S, you find out the absolute pressure divided by rho g. So this pressure head is there, plus the velocity head, because it is the total head, static head plus dynamic head. So half v square by g. Okay, this is the total absolute pressure head above the well, it has to be above the saturated vapor. So you have to subtract the saturated vapor pressure head. Okay, the word net implies a value above the vapor pressure. Okay, and positive implies absolute pressure and not gauge pressure. Okay, so you have to find out the absolute pressure head, absolute total pressure head. So the static pressure head plus velocity head at the suction point. From that you subtract the vapor pressure head. So you get the net value. So this is the net positive suction head. That is called NPSH. There are two NPSHs people talk about. One is the NPSH required for the pump provided by the manufacturer. For the smooth running of the pump, the NPSH minimum has to be maintained. NPSH A is NPSH available at the application setting. The rule is NPSH available should be greater than the NPSH required for the smooth operation of the pump. Okay, so there are two NPSHs. One is NPSH required for the pump provided by the manufacturer, and the next one is the NPSH available. That is the one available at the application setting where the pump is really kept for its duty. Now, determination of NPSH available. Okay, now see, you have a pumping setup. You have the suction point S indicated in the pump. A motor is there to drive the pump. Valve is there. Now, if you switch on, the pump must be working. So the suction head is HS. Now, I've shown a barometer, a water barometer. So in a water barometer, the liquid may go up to a height of 10.3 meters of water column. See, atmospheric pressure head. Okay, a long one, 10 meters means more than 30 feet. So that is given by atmospheric pressure by rho g. Okay, now this is the absolute head. Now we have to find out the absolute head at the point S. Now at the point S, the total head is again H0, that is, it's not P square, it is P by rho g plus V square by 2g plus Z plus the head loss. That is, the total head available in the system will be this one, and the total head, that is the Bernoulli constant. See, Bernoulli's equation, if you compare between 2 points, from the first point, if there is H0, in the second point you will have the values like P square by rho g at 2 plus B square by 2g at 2 plus Z2 plus the head loss between 1 and 2. Okay, Bernoulli's equation. So here the total head available is atmospheric head given by P atmospheric by rho g. So that must be equal to PS absolute by rho g plus Vs square by 2g plus Hs. Hs is the corresponding Z value. The Z is equal to 0 is the level at water surface. I have indicated Z is equal to 0. From that you measure. So the atmospheric pressure must be equal to the sum of all these. Now in the definition of our NPSH, you have to find out the total absolute pressure head at the point 2 and how much is it above H vapor pressure. Now the pressure, absolute pressure at the location S is P absolute by rho g plus Vs square by 2g, and that is equal to P atmospheric by rho g plus, minus HL plus HS. So you have to reduce the suction head and you have to reduce the head loss also. So next, the definition of NPSH available is P suction head absolute divided by rho g plus Vs square by 2g minus H vapor pressure. So that finally you will get NPSH is equal to P atmospheric pressure by rho g minus head loss minus head suction head minus vapor pressure head. You have to subtract all the three. Okay. Now based on this, we'll see a simple problem. A pump for which the critical cavitation parameter sigma c is 0.08 pumps against a total head of 60 meters. The water temperature is 35 degrees centigrade. The barometric pressure is 760 millimeters of mercury and the head loss in the suction pipe is 1 meter. Determine the maximum value of suction lift given vapor pressure head at 35 degrees centigrade is 0.58 meters of water column. Okay, so what is given is the head, the pumped by the pump is given 60 meters. Actually, that is used for calculating the NPSH required. Okay, you'll see in the next line. See, the critical cavitation parameter is defined like this: sigma c, otherwise called Thomas cavitation parameter. Okay, I have not written that. Thomas cavitation parameter, that is equal to NPSH required by H. So NPSH required is equal to H into sigma c. So head developed by the pump is 60 meters. So you get 60 into 0.08, which is the cavitation parameter. So you get 4.8 meters. That is the NPSH required for smooth operation of the pump. Now we will find out the NPSH available. So actually what is asked is what maximum value of suction head you can provide. Okay, so that suction head, that must be the available one maximum. So that is equal to P atmospheric by rho g minus H suction maximum plus HL plus H vapor pressure. So it will be equal to 10.3 minus the sum of all the three. So head loss is 1 meter, H vapor pressure is 0.58. Now you can equate these two. The required one calculated from the critical cavitation parameter, which is 4.8 meters, that is equated to the NPSH available. You have the simple equation. If you solve, you get HS maximum equal to 10.3 minus 4.8 plus 1.58. So you get 3.92 meters. Okay. So here you find the critical cavitation parameter sigma c, and the definition is that is NPSH required divided by H. Okay. Now we said that for the smooth operation of the pump, the NPSH available should be more than the NPSH required. Okay. If not, what will happen? What will happen is the phenomena cavitation will take place. So you might have studied about cavitation earlier, and I would say it is a destructive phenomenon that occurs in hydraulic flow systems or liquid flow systems. Okay, so not in compressed air systems, it is in liquid flow systems. What happens is in regions of low pressure like pump suction or water turbine exits, the liquid may boil with number of vapor bubbles that move with the flow and condense in another region where the pressure is little higher. In the region where the bubbles condense, excessive material damage occurs. Okay, this is cavitation. It has to be prevented. Now, this cavitation, when you want to say prevented, one is, you see that it doesn't cavitate. Then sometimes people manage cavitation by providing materials that can withstand the attack of the cavitation. So different materials are there which will give a long life even if there is cavitation. People also discuss whether cavitation is something chemical corrosive action or it is purely mechanical. So this place where the uh, bubbles condense, we say that the bubbles implode. The word implode is used. Implode is actually opposite of explode. So high pressure, small pockets explode, whereas these low pressure bubbles, they implode, they collapse. Okay, that is what I put as condense. So small bubbles and the micro movement of, I don't know what happens. It's really very difficult to physically imagine what is happening, but the result is the region, the pump means the pump body, cast in or any most of the materials, they will be eaten away as if there is a corrosion like thing. So there must be very very high pressure acting at that time, impulsive pressures and something like hammering. And two things, people talk about the effects. Okay, or one is the efficiency comes down, or maybe three things I can say. One is the efficiency of the pump will come down. The first one is probably the material damage. Material damage means, see, when a pump is bought or the pump is put into application at some site, uh, how many years you would like it to run without much maintenance?
10 years.
10 years is a good one. Maybe 5 years, 10 years, or 15 years. See, something about the way things work, how long. You can think of the refrigerator in your house. In many houses, they run continuously for 10 years, 15 years. See, there is a compressor inside. Maybe people say the machine that runs without any maintenance for a lot of years. They talk about the human heart, because for some people it runs up to 100 years without much maintenance. So these mechanical devices, refrigerator is one. In many houses they run for more than 10 years without much maintenance. Okay, so here it should run at least 5 years, 5 to 10 years. But a heavily cavitating pump impeller may run for a few months only and it will be eaten away. So material damage. Second one is the efficiency falls down. The third one, vibration and noise. So maybe these 3 points you have to write. Maybe I will write it in another this thing slide later. I think this one is the last one. Yeah. So now you can ask your doubts. You must be having some doubts.
Sir, in the pressure head versus discharge graph, which is the dependent variable,
I will
or
come
is
to
there anything
that.
like that? Yeah, this one.
Okay. Which is the
The red color line.
third one. That is for the pump characteristics.
Can
Okay. But
yeah,
one thing, have you done this in fluid mechanics lab or you missed it? Do you remember a little bit?
I don't think we plotted the graph. Not sure.
You ran the pump, isn't it? Yeah. Took some readings. Discharge you calculated maybe in the measuring tank. Vaguely remember?
Uh,
Okay. Now, see, when you this experiment, I think how it is done is you run the pump this is all constant speed, so you have pump running at constant speed. So you control the discharge by varying the valve position. So you have a set of variables, head and discharge. Now in mathematics, we always talk about independent variable and dependent variable, correct?
yes, sir.
Okay, where we plot the dependent variable,
Dependent is on y-axis.
Y-axis, that is the usual one. Independent in x-axis. So here we can't exactly say like that, but this is the way they have been plotted.
So
Because you know.
okay. So can we say that independent is actually the how much we are opening the valve, and that is changing this head.
Yeah, you can say it is in our control easily. So each valve position, I will get a discharge. That way also you can relate. So Q is the independent variable. Then correspondingly head and the full characteristics, you have all the three are there. Then you sit and calculate the efficiency. You will have some equation. Power, you will have the watt meter there for a few rounds. What is the time? Okay. Any other doubt? Okay. So I think we'll stop today. Okay. Today you do one thing. You send the quarter page. Okay. That is half page of some basic things which you have learned in the class, and whatever your questions and all those things. Maybe this will be taken as your attendance. Okay.
Okay, sir.
Yes.